Hello and welcome to OpenGL Oversimplified. In this video, I'm going to talk about depth testing. So imagine that we have a series of rectangles. Make them look nice. They don't actually have to look that nice. And they're drawn in front of each other. Now, the way they're drawn here, we can infer a natural sense of order. So if we were going from back to front, we would call these A, B, and C. Now, just a note on OpenGL's screen coordinates, the way they usually work. Typically, of course, X goes across, where on the left is negative, on the right is positive, and then right in the middle is X equals 0, and Y goes bottom to top, where the bottom is negative, the top is positive, and then somewhere in the middle is Y equals 0, so we'd have the center of the screen here, 0, 0. And this is the reason I'm talking about this, is a little bit tricky. So it turns out that Z equals 0 represents a depth in line with the screen, and then negative Z is something in front of the screen, so something that you can see, and positive Z is something behind you. Now, I see a lot of people saying this doesn't quite make sense. Shouldn't a positive Z be a positive depth, be a thing in front of me? And actually, I agree, that makes sense. So I want to talk about why that isn't the case. We have something in physics called the right-hand rule, which establishes our coordinate system. The way it works is if we curl the fingers of our right hand from one vector towards the other, so imagine that we are curling our fingers in a fist from X towards Y, then our thumb, this is bad. This is a bad drawing. Anyway, our thumb would point back towards us, and the direction our thumb points is the direction of the positive Z coordinate. And this works the same way. So if we were to curl our fingers from Y to Z, our thumb would point in the X. If we curled our fingers from Z to Y, our thumb would point Z to X, our thumb would point in the Y. So the reason that OpenGL adopts this slightly strange coordinate system is to be in accordance with the right-hand rule and make physical sense. A lot of systems like DirectX or Metal actually adopt a left-handed system. And so does Vulkan, actually, because it's easier to work with, makes more sense. Anyway, so if we look at our rectangles, let's say that I'll just give this back one a depth of negative 0.75, give this one a depth of negative 0.5, and this front one will give it a depth of negative 0.25. So you can see they're coming towards the viewer. If you're anything like me, you've played around with a bunch of visibility tests. You may remember the famous binary space partitioning that John Carmack developed for Doom, and you might be saying, hey, what really sophisticated trick is OpenGL using to determine visibility and intersections of these surfaces? And the answer is none. It is using brute force. So if I took these rectangles, I could draw them in a number of any order. I could do what's called the painter's algorithm, where I go from back to front, but there's no guarantee that the graphics card is going to see these rectangles in that order. We could rearrange that. So we could go A, C, B, 3 times 2 times 1. There are 6 possible combinations for draw orders that we could be seeing. So what I'll do is I'll go through an example of how OpenGL actually handles depth and objects using this BAC order. Okay, so I'll just color this in so we can see what these shapes should actually look like. Let's say C is going to be a pink color. And A is green. So if we were to draw these on the screen, this, whoops, went over the bounce there. If we were to draw these on the screen, this is what we would see. Okay, so let's set up our screen. And by the way, just remembering the order I'm going to draw these is B, A, C. So I'll set up the screen. I'll go 6 by 6. So OpenGL has what's called a depth buffer, and a depth buffer is simply a large array that stores a number for every pixel on the screen. And every time a pixel comes in, that depth buffer is tested. So at the start, before anything is drawn, I'm just going to be writing the depth values here. Okay, so at the start of every frame, the color buffer is cleared, so the color of the screen is completely cleared to some default, and the depth values are all cleared to some default as well. Typically, depth is normalized to a range of 1, so any depth further than -1 from the camera will not be visible, and of course, any positive depth will not be visible as well. So what we do is we have the first rectangle is B, and here we have all these pixels. So if we go, let's see, this is x equals 3, y equals 2, I guess. We'll go with that. 1, 2, 3, 1, 2. Okay, so this is the first pixel of B. Now this pixel is coming in at a depth of -0.5. So we compare -0.5 to the number which is in the depth buffer at the moment, and that number is greater than. So okay, yep, good, we'll update that. Now I'm not going to draw the colors in just yet. In reality, these colors are changing in the color buffer, but it's a little harder for me to rub out a highlighter. So for my purposes, I'm going to just do it this way and then color in at the end. So for each of these values, -0.5 is greater than -1, and so these regions are all colored and updated. Okay, the next one is A. Now, yeah, A is a 3 by 3. It has a depth of -0.5. So when we compare -0.5 with this pixel, that will get overwritten, as will this pixel and this pixel. Then we step down to the next row. Yes, yes, yes. Uh-oh. At the moment, the color here has an associated depth of -0.5. The incoming pixel has a depth of -0.75, so it's actually further away than the color which is currently written in the color buffer. Let's ignore that. No need to overwrite. And we'll proceed here and update the info. Okay, now the last one, C, is over here, and that is this region here. Now, if we look, -0.25 is better than all of these depths at the moment. So we will update all of those. Okay, so now I'll just go through and I'll shade in. Again, as I was saying, these color values are changing as the program runs, but it's just easier for me as a human to shade them in at the end. Okay, little messy, but there we have it. That is how depth buffers work. Now, this gives the key to the reason that the brute force approach is applied. Although it may not be the most elegant, honestly, I think it's pretty elegant. Although it may not be the most, sophisticated method, the fact is that writing to these pixels is an embarrassing parallel problem, because each pixel only depends on a bunch of local information. We have this array, these arrays that we're looking at, and we know exactly which element we're modifying. This pixel is not going to affect this pixel, and so modern graphics cards have something to the order of thousands of shader cores, and those shader cores can be scheduled with jobs to write all these pixels. So we can do it incredibly quickly. But there is something that we can do to speed it up a little bit. Notice that I was saying, as we come in and we write the first set of values, we are writing the color value as well. And then when we go to the next rectangle, we may be overwriting things which have already been written. That's not great. Well, it's even worse when we have lighting calculations to do as well, and we're doing, lighting calculations per pixel and then just overwriting that result. So one approach, which a lot of game companies go with, so there's deferred shading, but the issue with deferred shading, I said this was OpenGL oversimplified, so I'll give a simple version of deferred shading. Deferred shading is where you render your scene, but you don't do any light calculations. You just keep a track of all of the things that your scene can see. The color at each pixel, the perfect ideal color, the normal vector at each pixel, and all of that, all the information that you would need to later on do lighting. Then you take a snapshot of your scene, and then later on you have another pass where you calculate all of the lighting. But the problem with that is that in reality, storing information in a bunch of textures, it takes a lot of time to read and write, to copy textures, to do that sort of stuff. So another approach is something called a forward pass, or a Z pass. And what that is it turns out the fragment shader, the bit that writes the color information to the screen, is optional. You can ignore it. So typically you have a vertex shader, and your vertex shader applies all your transforms, and then we have a rasterizer. So with your vertex shader, you will just be working with the corners. But then when you pass it into the rasterizer actually breaks that info down and interpolates all of the attributes, including position, color, normal, everything, to get a set of discrete pixels. And then you'll have a fragment shader. And the fragment shader does the calculations and things. But in reality, that fragment shader is optional. You can get rid of it. All that means is you're not drawing anything to the screen. However, the depth buffer will still be updated appropriately. So the depth buffer will be updated appropriately. So imagine that I go and I draw these things again. However, the depth buffer is already waiting for me. It's already been set with the correct values. So when I go for this pixel here, I go, hey, this pixel's coming in at a depth of negative 0.75. Instead of previously, this would have a depth of -1 and it would come in and then be overwritten. Now it's saying, haha, I've done a depth prepass. I expect you have to be a depth of -0.5 or better. and you're not, so I reject you. And then lighting calculations are greatly reduced. The overdraw is greatly reduced. So that is just something to bear in mind. A depth prepass could potentially greatly improve your performance. There are other options. For instance, if you don't do a depth prepass, you could sort the models or the primitives in some way, but that's just a pain, so I would recommend that. Anyway, that'll be it for now. Hope you had fun. Hope you learned some things. Hope you can understand depth buffers a little bit more. I know they can be a little intimidating the first time you're looking at them, but yeah, all the best, have fun, and I'll see you again soon. Bye.